Okay, here's a little challenge problem for you. F of x is equal to the square root of 1 minus x squared, and we want to find f prime of x. So you're going to use the limit definition of the derivative, but we're combining a square root function and a polynomial function. Now, this has nothing to do with this problem, but it's a good opportunity to talk about it. Let's talk about where this function is defined, because if a function is not defined, then you can't find a derivative at that point. So let's think about this. We can't take the square root of a negative number. So what's going on here is what's under the square root right here has to be greater than or equal to 0 in order to be able to take the square root. So if we add the x squared over to make this a positive x squared, trying to solve for x here, let me flip this around because it's a little bit easier to think about. If x squared is less than or equal to 1, then we're good. X squared has to be less than or equal to 1. So let's think about what values of x will work here. Obviously, if x is 1, then 1 squared is 1. 1 is equal to 1, so we're good there. But let's think about, is it values less than 1 that are going to work, or is it values greater than 1? So let's just pick an easy one, 2. 2 squared is 4. 4 is not less than or equal to 1. So it must be numbers that are less than 1. So say, for example, 1/2. Okay? 1/2 squared is 1/4, and 1/4 is certainly less than 1. Now, we can't forget negative, though. Okay? Negative 1 squared is positive 1. So negative 1 works as well, and so does negative 1/2. Negative 1/2 squared is positive 1/4, so that's less than or equal to 1. So our function here is defined between 1 and negative 1, or in interval notation, it would look like this. So we can only use this function when our x values are between negative 1 and 1. So that means that if we find the derivative of this function, then we can only talk about it between negative 1 and 1. If they ask us, we're not to this point yet, but looking forward a little bit, if they ask you for the derivative of this function at 3, you can't do that because this function is not defined at 3. So this is kind of tying in why I was making you look at and analyze those domains of these functions, because you need to think about this before they start asking some of these questions, because they may ask you one where it doesn't even apply because that's not part of the domain. So just keep that in the back of your head. But I want you to pause the video, and I want you to see if you can find the derivative of this function. And I'm going to give you a second, pause it, you work it out, and then come back and watch me work it out. Okay, so we need to, I'm going to use h's. I like it just because I don't get my x's and delta x's mixed up, and it's one less symbol that I have to write down. So let's do this, 1 minus x plus h. Okay, I'm just finding my f of x plus h. Now, I could multiply this out and simplify some things, but I'm going to see if I can leave it in this form and see if things will work out. So let's try it. Let's try f prime of x is equal to the limit as h approaches 0 of our f of x plus h minus our f of x all over h. Okay, now this is no different from the problem we did before. We need to multiply by the conjugate. So we need to change the sign. We don't change any signs under our square roots. Okay, it's only that we change the sign between the square roots. And we do it top and bottom, but remember, we're not actually going to multiply it out on the bottom. We're going to leave it because hopefully some things are going to cancel out for us. All right, so still got the limit because we haven't done anything with it. When we multiply, remember the conjugate, what it's going to do is the square roots are going to go away for the first term here. So we've just got 1 minus x plus h squared. The outside and the inside cancel. We've got a negative times a positive, so that's a negative. Remember, we want some parentheses here because we're going to have to distribute that negative. Over h times 1 minus x plus h squared plus square root of 1 minus x squared. Now, we are going to have to multiply this expression out right here. Remember, that's x plus h times x plus h. It is not x squared plus h squared. All right? Because we can't simplify anything unless we multiply it out. So let's do that. We've got 1 minus, we got to put parentheses because there's a minus sign in front of this whole thing. So when we FOIL it, we get x squared plus 2xh plus h squared. And then I'm going to go ahead and distribute that negative for my last, for right here. Okay, I'm going to distribute that negative. And then again, just copying down this bottom. Be careful when you're copying. I have seen in the past so many careless mistakes, minuses that turn into pluses and vice versa, just when people have been copying things down. So please, please, please be careful with that and don't get lazy in those steps. All right, let's see what we can cancel. We've got a 1 minus 1 here. And if we distribute this negative, hopefully y'all be okay with me doing that without actually doing it, showing the steps. So we've got negative x squared plus x squared. So let's see what we've got left here. We have a negative 2xh. Okay, make sure you get that negative. And a negative h squared. And that's all in the numerator. And then we've got our denominator. Still hasn't changed. Okay. So we've got to get rid of that h. That's ultimately what we're always trying to get rid of. We've got to get rid of that. So how do we get rid of it? Well, we factor it. We factor it out in the numerator. So when we factor out an h, and I'm not going to worry about factoring out the negative. Normally I would, but I'm not going to worry about it right here because I don't have a negative h in the denominator I'm trying to get rid of, and I just about messed up. I almost lost my 1. See, I almost made the same mistake that I was warning you against. Don't lose that. Or no, I didn't. It is under the square root. I don't know why I was thinking it wasn't under the square root. Okay, now we can cancel out those h's. And I'm going to go ahead and plug in h at the same time because I am severely running out of room here. If I plug in 0 for h on the top, I've got negative 2x minus 0. So that's just a negative 2x in the numerator. And in the denominator, if I plug in 0 for h right here, well, look at what I've got. I've got 1 minus x plus 0. X plus 0 is just x. So I have the exact same square roots down there. So I've got 2 of them. And then we can cancel the 2's here. So here is our derivative. Negative x over 1 minus x squared is f prime of x. So kind of combined our polynomial with our square root function, finding the derivative there. So a little bit more intense than the ones we've done, but it's nothing out of reach. It's still using the same processes that we've been using up to this point. Okay, so you may need to go back and watch that because I know I did it kind of fast. You may need to look at some of the steps again. But like I said, it's the same thing that we've been doing. Okay, let's look at an AP question. The function f is continuous on the closed interval from -2 to 1. Some of the values of f are shown in the table below. So we've got values at -2, -1, 0, and 1, and our y values are -3, 7, k, and 3. It says the equation f of x equals 3/2 must have at least 2 solutions on the interval from -1 to 1 if k equals what? Well, think about, well, I'll give you a second. Pause the video. See if you can answer it, and then come back for my explanation. So we're talking about solutions. Solutions should make you think IVT. Okay, IVT is the whole idea that we can't skip values. So let's just take a second to sketch out what we've got. We've got at -1, 0, and 1. At -1, we're at 7. At 1, we're at 3. Okay, and it says our function equals 3/2. 3/2 is right here. So it has to have at least two solutions. So it means it's got to hit it twice between -1 and 1 is what they're wanting us to do. So if we start at 7 and we end at 3, to be able to cross 3/2, that must mean that we've got to come down, hit 3/2, and then hit it again on the way back up to 3. So let's see here. What would work for us here? 1. Okay, if 1 is less than 3/2, 3/2 is 1.5. Okay, so keep that in the back of your mind. If it's 1, if at 0 we equal 1, would that work? Yeah, because between 7 and 1 we got to hit 1.5, and between 1 and 3 we got to hit 1.5. So that would work. But let's just check, just to make sure. Check our other answer choices. Okay, 3/2 itself. Well, if at 0 we're equal to 3/2, we're not guaranteed that we're going to hit it somewhere else. So that's not enough. 2 doesn't work because 2 is bigger than 1.5. So that definitely doesn't guarantee that we would cross 1.5. 5/2 is the same boat. It's more than 1.5. It may cross 1.5. This may have a bunch of terms in it, but it doesn't guarantee it. Okay, so the only one that does guarantee it is 1. Okay, so let's talk. We've talked about the derivative in general. Okay, we've talked about the derivative in general, and the fact that the derivative gives us the slope of the tangent line at any point. Well, let's look at the derivative at a specific point. Say some x equals a, x equals 3, x equals 0, x equals -5. Okay, we're trying to find the value of the derivative at a point. We can modify our limit definition to do this. So f prime of a, okay, f prime of a is the derivative at a point. Up to this point, we've been doing f prime of x, derivative at x equals a, okay? At this point, we've been doing f prime of x, which just represents the derivative of the function, the overall function, but we want the derivative at a specific point on that function. So notice how our limit definition modifies. The limit as x approaches a, the value we're talking about, the point in question. X is approaching that value. So we're saying that we take the function minus the value of the function at that point over x minus that point. Okay, so let's look at this just very briefly. Let's look at a graph so we kind of know what's going on. All right, so here's just a basic quadratic negative leading coefficient because it's opening downward. Okay, so let's say we want to find not just the derivative of this function. We want to find the derivative right here at 2. Okay, so what this is saying is we're going to pick, what this limit definition is saying is as your x values get closer and closer to 2. So let's start kind of far away. Okay, let's start over here. Let's say that's our x value. So f of x is, I shouldn't have picked one that was directly parallel. Let's change that. Move it over just a smidge. Let's say right here. Okay, let's say this is our x. So here's our x. So f of x minus f of a over x minus a, what does that look like? How about slope? Okay, that's f of x, the y value at x, minus f of a, the y value at a, over x minus a. That is the slope between these 2 points. Well, what this limit definition is saying is as that x gets closer, let's pick a different one, x1, as that gets closer to a, the slope between these 2 points is going to be closer to the slope just at that one specific point. Remember, that's what we said that the derivative was, the slope of the tangent line, that line that only touches the curve at that one point that's perpendicular to that curve. So see how those slopes change from the purple to the green to the blue. It becomes more steep, which is at A, at 2, I picked 2 in this case. At 2, that part of our parabola was pretty steep, okay? So that's what this is talking about. That's why this limit definition works, Okay, so let that sink in for a second before you go on. Another vocabulary you need to be familiar with is that the derivative is also known as the instantaneous rate of change. So we've talked about average rate of change being slope, okay, average rate of change being slope. Well, instantaneous rate of change is the derivative. Instantaneous rate of change is the derivative at a point, okay? So f prime of a instead of f prime of x. So the words derivative, slope with a tangent line, instantaneous rate of change, all those should be synonymous in your mind, okay? All those are derivative, slope of the tangent line, instantaneous rate of change. Those should all be synonymous in your mind. Okay, so let's take an example here and put the two ideas together. We're going to find the average rate of change. Okay, again, that should be saying slope. Okay, average rate of change. Anytime you read that, circle it and write slope. Okay, you got to know that. You got to be thinking that. Of the function over the given interval, and also find the instantaneous rate of change. Circle that and say derivative at the extreme values of the given interval. So let's start with the average rate of change. That's really easy. It's the slope. So we're given an interval. Remember, these are the x values, x1 and x2. So they didn't give us the y values. They did not give us points. They gave us an interval. So we've got to find the y values to begin with. So f of 5, square root of 4 times 5 minus 7. So that's 20 minus 7, that's the square root of 13. Yes, they expect you to be able to deal with square roots, okay? And they also expect you to deal with fractions a lot. They love fractions, and you should too. 4 times 11 over 2, okay? 4 over 2 is 2. 2 times 11 is 22. 22 minus 7 is 15. So that's the square root of 15. So those are our y values. So average rate of change, and delta represents change, so I'm going to abbreviate here. Average rate of change equals y2 minus y1 over x2 minus x1. Now, we can't do anything with those square roots. We can't combine them, so let's just leave them as is. 11 halves minus 5. Let's think about what 11 halves is. 11 halves would be what? 5.5? 5.5. 5.5 minus 5 is 0.5, so that's 1 half. Or you can do it from a fractional perspective. You can do that as well. 5 as something over 2 is 10 over 2. So 11 over 2 minus 10 over 2 is 1 over 2. But they do use fractions, so you got to get used to fractions. So if you need to figure it out using decimals, that's fine, but you need to convert your decimal to a fraction. Okay, and then dividing by 1 half is the same as multiplying by 2. So we've got 2 times the square root of 15 minus the square root of 13. So that does need to be done without a calculator, but I'm going to want to compare this. Okay, I want to compare this average rate of change to the instantaneous rate of change. So I'm going to go ahead and give my decimal approximation here, just so that I do have something to compare it to here in a minute. Okay, so 2 times the square root of 15 minus the square root of 13 is approximately 0.534. This is a good time to talk about, on the free response part of the exam, how they want you to round. Key number 1, always, always, always 3 digits after the decimal. Always, always, always. So when you have a calculator active problem and you get a decimal, which I guarantee you will at some point in time, you always, always, always round to 3 digits after the decimal. Now, you're probably thinking, Ms. Redmond, do you remember your rounding rules? Because shouldn't that be 0.535? You are correct. If you're rounding, yes, it should be 0.535. But the wonderful AP people thought that it would be a good idea to allow us to what they call truncate numbers. Okay? So that means you really don't have to worry about rounding rules. All you have to do is write the first 3 digits after the decimal, and that's it. You stop. Don't do anything else. Write the first 3 digits after the decimal, and you're done. That's all you have to worry about. First 3 digits after the decimal, stop. Don't worry about rounding, because guess what? If you misrounded that, which, I mean, it pretty much what it does is they don't have to take off points for kids that can't round, okay? Because you're either going to put 0.535, which is the correct rounding, or you're going to put 0.534, which is the incorrect rounding. But they decided, I guess so many kids were not rounding correctly, that they decided, well, instead of not giving them the point for this entire problem just because they didn't round in the last step, let's just let them truncate it. We'll count either rounding down or rounding up. So they call it truncating just to make it sound a little bit fancier. But again, first 3 digits after the decimal and stop. Don't worry about rounding. Just stop. First 3 digits and that's it. Now, if you want to write more, you can write more, but there's no point in writing more. They want 3 digits, and that is sufficient enough for them on all problems. Nothing less. Do not put 2 digits after the decimal. I will come over there and I will pinch your head off. I will find you wherever you're at. 3 digits, always, 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 always. Yes, that sounded harsh, but I want you to remember 3 digits after the decimal. Okay? So, anyways, a little bit of a rabbit trail there, but it's okay. We needed to know that little lesson, and I will bring it up again, I promise, in the future. So that's the average rate of change over this interval. The second part of the problem, they asked us to find the instantaneous rate of change, which should make us think derivative at the extreme values. So we need to start with the derivative. We need to find the derivative of this function. So remember, we've got to do f of x plus h, which in this case is 4 times x plus h minus 7. If you want to, you can go ahead and multiply that out, because we're probably going to use it later on. So 4x plus 4h minus 7. Okay, so f prime of x equals, you know what? Sorry, the whole point of this is to use our new limit definition. I apologize. Let's look back at our new limit definition. The derivative at a point. Okay, the limit as x approaches a of f of x minus f of a over x minus a. So let's do that. Okay, let's use our new limit definition. So f prime of 5, okay, f prime of 5 is the limit as x approaches 5 of f of x, so just the square root of 4x minus 7, minus f of a. Well, guess what? We already figured that out. We already figured that out a second ago. It was the square root of 13 over x minus a. Now, guess what? We still have the same problem. We still have the same problem. If we plug in 5, look at what's going to happen. We're going to get the square root of 20 minus 7, which is 13, minus the square root of 13, which is 0, over 5 minus 5, which is 0. So, guess what? We have to conjugate. Again, we're not changing the signs under the square root. We just saw, whoops, not changing it yet, sorry. Okay, this is my original. Here comes my conjugate. Plus the square root of 13. Again, don't multiply out bottom. Do not multiply this part out, because it's going to, something's going to cancel here in a second. All right, so let's check it out. When we FOIL, square root of 4x minus 7 times square root of 4x minus 7 is 4x minus 7. The outside and the inside cancel, and then we've got minus 13. And you're probably thinking, well, this isn't looking like our other problems have. Well, sit tight for just a second, and it almost is. What's negative 7 minus 13? Negative 20. What can we factor out of that numerator there? We can factor out a 4. And what are we left with? X minus 5. So, whoops, and I don't know why, I think because I was thinking about it canceling, I didn't write it. Now we can cancel it. So, I'm going to plug in 5 because I just removed the problem. 4 over the square root of 4 times 5 minus 17 plus the square root of 13. So what do we get? 4 over 2 square roots of 13. 4 times 5 is 20, minus 7 is 13. Square root of 13 plus square root of 13 is 2 square roots of 13. So this is 2 over the square root of 13. That is f prime of 5. That is the derivative at 5. That is the instantaneous rate of change at 5. That is the slope of the tangent line at 5. So let's compare that value to 0.534. Let's look at its decimal approximation. 2 over the square root of 13. Pretty close, okay? Pretty close. 0.5547, okay? Pretty close. So let's do this for 11 halves. Ooh. Okay, let's do this whole process again for 11 over 2. So just to give us practice here with our limit definition at a point, f prime of 11 over 2 is f of x, the square root of 4x minus 7, minus f of a, well, what was that? That one was the square root of 15. Okay, over x minus a, which is 11 halves. So multiply by the conjugate for square root of 4x minus 7 plus the square root of 15. Hopefully you're catching on to the fact that the same thing happens every time. So you may be able to skip some of these steps, but I don't want you to get too happy with that. That's why I haven't really mentioned it up to this point. Okay, so let's see here. Whoops, I left out my limit. Not good. The limit as x approaches 11 over 2. This is the limit definition after all, right? The limit as x approaches 11 over 2. We get 4x minus 7 on the top minus 15 over x minus 11 halves. Now you're probably thinking, how is she going to make this one work out? Guess what? We get to do some creative factoring. All right. Negative 7 minus 15. That's negative 22. Okay, now, you're used to a GCF, the numbers have to be completely evenly divisible, right? Well, guess what? I'm going to take out a 4, even though 22 is not divisible by 4, because guess what? When you divide 22 by 4, you get 11 over 2. And that's exactly what we need it to be. Isn't it beautiful how these problems work out this way? It's amazing what people figured out a long time ago before they had even a fraction of the technology. I mean, they had no technology when they figured this stuff out. So I could have gone ahead, and I was so focused on the beauty of it, I wrote out an extra step. That's all good. Okay, now we can plug in 11 over 2. 4 times 11 over 2 minus 7 plus the square root of 15. So guess what that gives us? 2 square roots of 15 on the bottom. So that gives us 2 over the square root of 15 is f prime of 11 over 2, which is the derivative of f at 11 over 2, which is the instantaneous rate of change of f at 11 over 2, which is the slope of the tangent line of f at 11 over 2. Y'all probably think that I'm crazy with the way that I'm emphasizing some of this stuff, but I've been teaching this for a while, and I know what people continue to forget, so I'm going to do my best to emphasize the things that people forget. All right, so that's approximately 0.516. I didn't write the other one down, but it was approximately 0.554. Okay, notice how the average rate of change is between those two numbers. Okay, interesting thought there. And all three of those numbers are pretty similar because this wasn't a very long interval. We were going from 5 to 5.5. So those are pretty close to each other. If our interval was bigger, if we were going from maybe 5 to 7, you would have seen a bigger range of those values because they're further apart on the graph. So those instantaneous rates of change aren't going to be as similar because they're further apart on the graph. Pause the video and let that one simmer for a minute, okay? Okay, so a little bit of practice here. Find the instantaneous rate of change of these problems. We did a square root problem, but here's good practice with our limit definition with rationals and with polynomials. Use the new limit definition to find the instantaneous rate of change at a given value. So do these problems, and then I would also like for you to do textbook page 131, 5 through 9 odd, and I will put the answers to these problems on here really quickly so that you can check those as well. So, well, I probably should. I'll have to look at the answer key, okay, so that I can put them on here quickly.